Okay, this is going to be a second day of material on Green's theorem. So we are going to look at more challenging examples. But let's just review what Green's theorem, at least one version of Green's theorem, says in one of its most simple forms. There's actually lots of variants of Green's theorem. Let's not overdo it right now. Let's just get a reminder of what we had seen last time. So if D is a simply connected two-dimensional region in the plane, and C is the boundary of D. In notation, what we write for this is C is equal to, and then this symbol looks like partial derivative symbol is what we write for boundary of. So C equals boundary of D. And C is oriented counterclockwise. Then the integral over C of P dx plus Q dy is equal to the double integral over the two-dimensional region D of partial derivative of Q with respect to X minus partial derivative of P with respect to Y dA, D capital A. And just a reminder of some notation things. You really don't need to think about this or read this really all that differently, but sometimes when you do have a closed curve, so the boundary of a two-dimensional region, you're going to get a closed curve. So sometimes there's a little just circle drawn as part of the integral symbol. So you don't really need to worry about reading this really any differently. Okay, so this notation is used either with a circle, as we saw here, as we see on this line, or sometimes that circle even has like a little arrow just as a reminder of the direction. Okay, to indicate the counterclockwise orientation. Otherwise, sometimes maybe you want clockwise. So if you do, then what? Things get a little trickier. Usually it's just described in words. Now this phrase simply connected over here, that's actually new. We did not introduce that last time, but that's so far we've only looked at simply connected shapes, and we're going to start looking at non-simply connected shapes. So let's just clarify what this means. D is simply connected. Informally speaking, it just means that there's no holes. It's kind of funky language. How did that become no holes? We're not going to get into it right now. Let's just draw a picture. If you have a region that's like this, completely filled in, then this is D is simply connected. However, if we take a region like that, and then there's that spot in there, and we're going to shade in this part. Okay, but there's this like left over, there's this hole in the middle right here. Let me undo that. So we have intentionally not shaded in that hole. This is an example of D is not simply connected. So I hope the informal language of no holes is helpful. We are going to, by the end of today, talk about how do we do Green's theorem in that kind of situation. We're going to have sort of a variant, if you will, of Green's theorem. Now, what if you notice that we set up here that you have to have oriented counterclockwise, but what if C is clockwise? What if C is oriented clockwise? There's a way to deal with that. Not from the theorem directly, but sort of after applying the theorem. So what do you need to do is you really just need to go in reverse and negate the integral. Negate the integral. Let's talk about what that really looks like. In other words, you've got integral, so say your C is clockwise, P dx plus Q dy, and then, sorry to be a little informal with our notation, but this will be the negative of, if you integrate well, negative c here is our way of just trying to say go in reverse. Okay, p dx plus q dy. This is, what's this like? So I know this seems a little, okay, the minus, we know what negative does here, okay? Sorry for the quick informal notation of that minus in front of the c, just meaning travel along c in the reverse direction. But what is this like? This is actually like something from your Calc 1 class. Integral a to b of f of x dx is equal to negative if you swap the endpoints of integration. Integral from b to a of f of x dx. And it really is sort of fundamentally for the same reason, and we're not going to get into those details exactly why and so on and so forth, but just treat it just like that. So let's look at an example. Let C be the clockwise, ooh, we're already getting started with this, the clockwise circle of radius 2 centered at the origin. Then we're going to find the integral over c of x to the power sine of x plus 3y dx plus quantity 10x plus root y to the fourth plus 1 dy. Okay, and then just because I don't want to deal with the clockwise, let's just let capital B be the counterclockwise circle. So following our informal notation earlier, capital C equals negative B, you could write capital B equals negative capital C, and then the integral that we were asked to compute over C of x to the sine x plus 3y dx plus quantity 10x plus root y to the fourth plus 1 close parentheses dy is equal to negative integral over b of x to the sine x plus 3y close parentheses dx plus quantity 10x plus root y to the fourth plus 1 dy. So that minus sign is included because we have b instead of c. But now the point is that we have something where we're ready to go now that there's a b here. So let's just maybe make some mentions here that one thing we could do technically, method 1, technically, we could take b, we could parameterize b, and it wouldn't be hard to do, right? B is oh yeah, circle, now counterclockwise, radius 2. I mean, it really should just be x of t is equal to 2 cosine of t, y of t is equal to 2 sine of t, and t goes from 0 to 2 pi. And then if we were to write this out, okay, this integral here, it ends up equaling, let me just get the, well, let me erase that equal sign. I'll do that. Okay, this ends up equaling, let's see, integral, so let's copy the minus sign first. Okay, minus sign, integral, t value 0 to 2 pi. We should take this thingy here and replace all the x's and y's we see with 2 cosine t and 2 sine t. So let's do that. So we'll have here 2 cosine t raised to the sine of 2 cosine t plus 3, okay, there's a y that we need to replace with 2 sine t. Dx gets replaced with the derivative of x followed by a dt. So we differentiate 2 cosine t. We'll have here a negative, let's see, make sure to get some parentheses here. First close those set of parentheses. Okay. Then dx over dt would be negative 2 sine t, and then we need to include a dt, plus the second integral for this next part. So we've got an integral, let's make sure, actually, that minus sign carries properly. So how about we just use a huge set of square brackets here. Another integral, t going from 0 to 2 pi of 10 times, and then x is going to be replaced with 2 cosine t plus root y to the fourth. So it's 2 sine t, quantity to the fourth plus 1. We can close these parentheses. The dy here needs to become dy over dt, which is 2 cosine t, and then times a dt. Okay, so cool. There's two integrals that look really messy to do, right? So we could try this, but let's just say, ugh, yuck, don't want to do that. So method 2, instead of doing these integrals, so now that we have b traveling, b is traveling in a counterclockwise direction, we can talk about d. D is a disk of radius 2. So it's the filled-in circle of radius 2. And we can say that the same integral that's over back here, okay, it ends up, sorry for the arrow here, equaling the double, let's copy the minus sign. Sorry about that. Let's just copy this minus sign. Let me circle it in green here. We've copied on the minus sign first. And then we have the double integral over d of, well, we need, if we go back to what Green's theorem says, we need the partial derivative of q with respect to x, and then we need to subtract the partial derivative of p with respect to y. So take a look at q, which is right here, 10x plus root y to the fourth plus 1. When we differentiate that with respect to x, we just get 10. This next part, the radical with the y inside and whatever, that, remember, y is constant right now, so that part just differentiates it to 0. Then we need derivative of p with respect to y, so p is over here, x to the sine x plus 3y. When you differentiate that with respect to y, remember x's are constant, so we just actually end up with 3, okay, dA. Okay, this looks nice, yeah? Let's actually now convert this to polar. So let's first just copy the minus sign. That we will circle that in green again, okay? And then we'll have integral. We're integrating, let's say 10 minus 3 simplifies to 7. But the thing to do really is to convert this to polar, right? Because we're talking about a filled-in circle now. Yeah, if we didn't draw a picture, but d is a filled-in circle of radius 2. So doesn't it make sense to change the dA to become r dr d theta and have r go from, not there, have r go from 0 to 2 and have theta go from 0 to 2 pi. And when all is said and done, we'll skip all the work for this, but you can work this out. There's not a bad integral to actually do. You'll get negative 28 pi from doing this. So here's the thing. Sometimes it's nice to turn integral over a curve C, over a closed curve C, p dx plus q dy into a double integral over d of some stuff using Green's. Yeah, so using Green's theorem. On some level, it doesn't really matter if C is oriented counterclockwise or clockwise. Of course, to apply the theorem as we directly stated it, C needs to be counterclockwise, but we saw just in this example, you can switch the direction of the parameterization, or the orientation, I guess you could say, and then at the cost of this minus sign that we kept seeing floating around, just circled in green several times.